Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of real analysis. From the couple of lecture we are discussing properties related to supremum and infimum of a set. In today's lecture we are going to discuss an important property that is related to the infimum of a set. The statement of the property is: if S is a non-empty subset of R that is bounded below, let A is any real number, define the set A plus S, which is actually the sum of the elements of S. Sorry, here S belong to capital S, and A is any real number. That is, set A plus S is actually can be formed by adding or increasing the elements of the set S by A. We need to show that the infimum of A plus S is equal to A plus infimum of S. To follow this class, I hope you are familiar about the concept of lower and upper bound of a set, bounded above and bounded below sets, and supremum and infimum of the set. So here what does infimum of A plus S shows? Actually, infimum of A plus S means this is the greatest lower bound of A plus S. Infimum of A plus S means shows this is the greatest lower bound of A plus S. So to prove this property, we assume proof. Firstly, it is given that since it is given that S is non-empty set and this is a subset of R, and S is bounded below. S is bounded below. We know that a set is called bounded below if it has a lower bound. This implies S has lower bound. Further, since R is a complete ordered field, R is a complete ordered field. So, by definition of complete ordered field, the supremum and the infimum property must exist in R. So here the greatest lower bound property of R says that as S has a lower bound and R is a complete ordered field, this implies lower bound infimum of set S exists in R. So let us assume that the infimum of the set S is, let infimum of set S is equal to U. By definition of infimum, what is the definition of the infimum? Infimum of a set S is a real number that is less than or equal to every element of set S. So by definition, as infimum of this set S is U, so U is less than or equal to every element of set S. So we can write it as infimum that is U here is less than or equal to set S. By adding A on both sides to form the expression, required expression, here you can see we are adding a with infimum of s. So adding a on both sides of this expression, we have a plus u is less than or equal to a plus s. Now, a plus s are the element of, as a plus s is the element, arbitrary element of set a plus s. So inequality 1 shows that there is a number a plus u which is less than or equal to every element of set a plus s, because a plus small s is the arbitrary element of a plus capital S. This shows that a plus u is less than or equal to every element of a plus s. If a number is less than or equal to every element of set a plus s, then that number is called lower bound of set a plus s. This implies a plus u is lower bound of set a plus s. But we need to show that a plus u is the greatest lower bound of set a plus s. You can see at the start, we have to show that uh, infimum of a plus is s is equal to greatest lower bound of a plus s. So now the lower bound of a plus s is here. A plus u is the lower bound of set a plus s. To prove the result, we need to show that a plus u is the greatest lower bound of a plus s. We show that a plus u is greatest lower bound of set a plus s. For this we take v as another lower bound of set a plus s, and we show that this v is smaller than or equal to a plus u. This will show that a plus u is the greatest lower bound. So to our target is to show this expression. So as v is lower bound of set a plus s, this implies by definition of lower bound, v is smaller than or equal to every element of a plus s. This implies v is less than or equal to every element of set a plus s, where a plus s belong to set this for all a plus s. By subtracting a on both sides of the expression, we have v minus a is less than or equal to s. Now from this inequality, you can see that s is the arbitrary element of set s. On the left side, the number v minus a is less than or equal to element of set s. If a real number is less than or equal to every element of set s, then it means v minus a is the lower bound of set s. As s is less than or equal to s, so from 2 v minus a is lower bound of set s. We know that a number is called lower bound if it is smaller than or equal to every element of set s. As small s is the arbitrary element of the set s, this shows that v minus a is the lower bound of set s. Further, we know that lower bound is always less than or equal to greatest lower bound. This implies v minus a is the lower bound of set s. This implies v minus a is less than or equal to greatest lower bound of set s. This implies V minus A is less than or equal to, what is the greatest lower bound of set S? The greatest lower bound of set S is, greatest lower bound of set S. This is U. U is infimum of S, and infimum of S mean greatest lower bound of S. So U is the greatest lower bound of set S. So the greatest lower bound of S mean infimum of S, and infimum of S is U here. So V minus A is less than or equal to U. This implies by adding A on both sides of the expression, we have V is less than or equal to A plus U. That is our requirement. This shows that V is the lower bound. V was the lower bound. V is the lower bound of set A plus S, which is less than or equal to an other lower bound of A plus U. This implies A plus U is the greatest lower bound of set A plus S. As here we assumed V is another lower bound of set A plus S, and A plus U is also the lower bound of set A plus S. Now as V is smaller than or equal to smaller than or equal to A plus U, this shows that A plus U is the greatest lower bound of set A plus S. Or in other words, we can say that A plus U is the greatest lower bound of set A plus S mean infimum of A plus S is equal to A plus U. What does this expression shows? A plus U is the greatest lower bound of set A plus S. Greatest lower bound of A plus S. Greatest lower bound of A plus S mean this can be written as infimum of A plus S. And infimum of A plus S is equal to A plus U. Lastly, by substituting or replacing U, and U is infimum of S, which is required to prove. So I hope after the total lecture you have a clear understanding about this property. Inshallah, in the next lecture we will discuss some other properties related to supremum and infimum. Until then, take care. Allah Hafiz.